Okay, so right, so this is about the definition of a vector space. Okay, so we have these two operations, which of course satisfy a bunch of axioms. So satisfying the following. Okay, so and I'm sure you all have seen this and probably remember it very well, but I want to make sure we're on the same page. Okay, so it satisfies a bunch of axioms, including the commutativity of addition. So x plus y is equal to y plus x for any two vectors. We have associativity, so it doesn't matter in which order we add three things. You can take x plus y and then add z to it, or you can take x and add y plus z to it. So associativity. There exists an element 0, a special vector, the 0 vector, such that if you add it to any vector, you get the same vector. And this holds for all x and v. Yeah. Now, we also have that for each x in V, there exists an element y in V, a vector in V, such that the sum x plus y is equal to 0. So this means that y is an additive inverse of x, right? Now 5, we have that multiplying by 1, the scalar 1 in the field. So if you scale any vector by 1, it doesn't change. So 1 times x is equal to x for all x and v. What else do we have? We have similarly distributive laws connecting so first of all, we have that multiplication is also associative. So a times b times x is the same thing as a times b times x. So note that in the first case, I'm multiplying my vector x by scalar b, and then multiplying by scalar a. But here I first multiply the scalars in the field, right? So it's just multiplication of two numbers in the field. And then I multiply the vector by it. So we have that this holds for all a, b scalars in f and x a vector in v. And now we see how the two operations are connected. So I can multiply the vector x plus y by scalar a. This is the same as multiplying first x by a and adding it to the vector y multiplied by a. Okay. And finally, we have that a plus b. So if I take the sum of two scalars in my field and multiply the vector x by it, then it's the same as a times x plus b times x. Okay. So all of this hold for arbitrary choice of a, or here I should have said b as well. Yeah. So for any two scalars a, b, and f, and any two vectors x and y. Okay. So this is a bunch of properties, which of course you're familiar with. These are the axioms of vector spaces. Okay. Anything satisfying it is a vector space. And as usual, we refer to the elements of V as vectors and the elements of F as scalars. Okay. All right, so this is the most important definition of the course. Of course, we've gone quite far from it in 115a. But let's first record, to make sure that we're all on the same page, some of the basic properties of vector spaces. Okay, so how these operations interact. So we had so-called theorem 1.1, the cancellation law. And my numbering, by the way, will correspond to the numbering in the textbook to make it easier for reference. If you want to look up the proof or more information, more examples, yeah. So first of all, there is a cancellation law. So if V is a vector space, then for any x, y, z in V, we have that if x plus z is equal to y plus z for the same z, right? Then in fact, we have that x is equal to y. So we have cancellation with respect to addition of vectors. So this, of course, easily follows from the axioms of the vector space. I'm not going to present the proofs in this discussion part, in this revision part, yeah. But yeah, again, you can, if you're asked with this kind of arguments, you should play with it a bit. I think it will be helpful. Okay, so an immediate corollary of this is that in any vector space V, there exists a unique element 0 satisfying the axiom 3 from the list I just gave you. Yeah. So let me go back for a second. So you see axiom 3 here. We say that exists an element such that it's neutral under addition. So adding x to 0 is x for any vector x in V. From cancellation, we immediately see that it's unique. There's exactly one element with this property. This is 1 and 2. So for all V, a vector space, and for all x in V, there exists also a unique element y in V, satisfying axiom 4. So axiom 4 is about inverses. Yeah. So what we are saying is that each element has a unique inverse. Okay. And since it's unique, we'll be calling it called the inverse of x and denoted minus x. Okay. Yeah. So it's just notation. Yeah, we have each element has an inverse. We denote it as minus x. Okay. Good. So let's summarize some more properties of the operations. So let V be a vector space over F. And by the way, I might not say this every time. Yeah. So let's agree that capital V will always denote a vector space, and the field will be denoted by capital F typically. So we have that for all x in V and for all A in F, the following properties hold. So first we have that if I multiply any vector by the scalar 0 in F, then I get 0. Yeah. So here it's important to distinguish, like I said, that this is a scalar. So this is an element of the field F, but here it's the 0 vector in V, right? Okay. So multiplying any vector by the 0 scalar gives us a 0 vector. 2, if I multiply a vector x by minus a, where a is a scalar, so it makes sense to talk about minus a in the field, of course. So I get minus a times x, and this is the same as a times minus x. Yeah. So here again, note that this is, for example, minus x is the vector in V, the inverse of x. But here this is in F, right? So this is just a number. For example, if the field is reals and a is a real number, then this is just minus a for that real number. Okay. And here again, this product is an element of V. So it's important to keep track of, in such calculations, to keep track of which sorts the objects are in. Okay. Oh, sorry, I see there are some comments in the chat. Let me look it up. Sometimes I might not notice it. So if you see I'm not reacting to what you asked in chat for some time, just turn on the microphone for a second and let me know, okay? Because I don't look every second at the chat. Yeah, so sorry, this notation. So when I write exists with exclamation sign, this is just an abbreviation for there exists a unique blah, yeah? So in this case, the element with properties given by the axioms for the 0 vector, there's only one in any vector space. And similarly for the inverse, there is only one, okay? Yeah, so it's just a notation to abbreviate this, exists unique. Okay, okay, good. So let me go back to this theorem, which connects some of the properties of the operations. So 3, we have that a times the 0 vector is still the 0 vector for all a an element of the field F, okay? So multiplying the 0 vector by anything, we still get the same 0 vector. So let me again stress that here in both cases, this is the 0 vector, right? So this is an element of V. But A, on the other hand, is an arbitrary scalar in the field. Okay, So again, all of these quickly follow from the axioms, but you can either look it up or you can, to refresh your memory, you can work them out yourself. I think it's a good first exercise, a good warm-up. Okay, so we have these basic properties of the operations on vector spaces, okay? All right, so like I said, the main subject of study of linear algebra is the category of vector spaces. So we have this collection of vector spaces, and we want to understand two things: how operations on a given vector space behave. So for this, we have a number of results. We also want to understand how different vector spaces can interact with each other. This is point 2. And of course, point 3 is that there are many applications. We want to study specific vector spaces and want to understand how general theory applies to give us more information about the specific vector spaces, okay? So this is a summary of what I just gave you, the summary of the basic properties of operations on the vector space. Next, let's talk about how two different vector spaces can interact. And the very first question to understand here is when we are given this class of objects, all vector spaces, we want to understand how one vector space can sit inside of another. Okay, so what does it mean? So this leads us to the discussion of subspaces, of vector subspaces. Okay. So what is a subspace? Let me remind you. So definition, let V be a vector space over some field F, then a subset W of V is a subspace. Okay, so remember that subset is just a collection of elements of V with no additional requirements. Okay, but now we want to impose some requirements, in which case we can refer to such a subset as a subspace of V. If we have that W itself is a vector space with respect to the addition and scalar multiplication on V. Okay, so again, what do I mean by this? So let's recall, we have, assume we're given this vector space V, right? And we're given some subset W. So what we mean for W to be itself a subspace, to be itself a vector space with respect to the same operations that we were given on V, it simply means that it satisfies all the 9 axioms that we listed, right? If now I look at this W, if I am given 2 elements of W, the in particular elements of V, of course, right? So it means that the sum for these 2 elements is defined in V. So if this is, for example, X, this is Y, then we have the element X plus Y, a vector in V. But a priori, it doesn't have to be in W, right? If X and Y were in W, it might be outside of W, for example. So one axiom then must guarantee, when W is a subspace, that the sum is inside the vector space, W itself, right? Okay, so let's make this more precise. Well, and there are some other conditions. So let's summarize all the conditions that we need to ensure that W is a subspace. So this is theorem 1.3. So assume V is a vector space and W is a subset of V. Okay. Then W is a subspace of V if and only if the following 3 conditions hold. So A, the 0 vector is in W. B, X plus Y is in W for all XY in W. Okay. We refer to this by saying that W is closed under addition. So somehow when you keep adding vectors in W, you can never get outside of W, okay? And finally, it also has to be closed under scalar multiplication, right? So we have that C times X is in W for all C in F and all X in W. And to this property, we refer by saying that W is closed under scalar multiplication. Okay. So this theorem gives us a simple criterion to test when a given subset is a subspace. Yeah. Instead of checking all the 9 axioms, all you have to verify is these 2 properties. And then this theorem, the proof of the theorem establishes that these 3 properties alone are sufficient to ensure that all the other axioms also hold for W. Okay, so it's a very important result for determining when a given set is a subspace and when it's not, of course. Okay, all right. And one important property of subspaces of a given space is that we can intersect them to get a new subspace. Okay, so let V, this is theorem 1.4. So let V be a vector space over some field F. Okay, now if I give you finitely many subspaces, W1, W2, etc., Wn, if they're all subspaces of V, okay, then the set W, which is given by the intersection of this, so W1, intersection W2, etc., intersection Wn. So then this intersection is also a subspace. Okay. Either in the notes or in the book, because yeah, it's instructive to see how these 3 conditions are necessary and sufficient to satisfy the axioms of vector spaces. Okay. All right. So this is 1.3. And for 1.4, so the point is that if I give you a bunch of sets, all of which are closed under addition, multiplication, scalar multiplication, and contain the 0 vector, then the intersection of the sets also has the same property. Yeah. So subspaces are closed under intersection. It gives us a general way to sometimes get new spaces from some given ones. Okay. So these are some comments about subspaces. We'll need more of them, but these 2 theorems are the most important things to remember as we move on. Okay. Any other questions about these 2 results so far? Okay, seems not. So then let's move on to the next topic, linear combinations. Okay. So this is, of course, a very important topic, which allows us to study subspaces in more explicit way, to talk about spans and to talk about linear independence. All of these are central notions in understanding the structure of vector spaces. So let me remind some of these notions quickly. So definition. As usual, let V be a vector space, okay? And let S be a subset of V, which is non-empty, okay? So S is a non-empty subset. So I'm not requiring it to be a subspace, just an arbitrary subset, which contains at least one vector, okay? Then a vector V in the space, capital V, is said to be a linear combination of S, or sometimes we can say a linear combination of the vectors in S, if one can write this vector V as the sum of the form A1 times U1 plus A2 times U2 plus etc. plus AN times UN for some vectors U1 through un in S, in the set S itself, right? And some scalars A1 through AN in the field of scalars F, okay? So a vector V is linear combination, if we can write it as a sum of vectors from S, the set we're starting with, and arbitrary coefficients, yeah, arbitrary scalar coefficients applied to them. Okay. All right. So somehow this means that the set S can see this vector V. Yeah, it's possible to express this V in this form using vectors in S. So this is one. And two, using this, we can define the span of this set S, which is denoted typically as span S. This is the subset of V consisting precisely of all linear combinations of S. Okay. So we look at all vectors that can be obtained as linear combinations of S, and we collect them all together in this set. Yeah. So in other words, we can write it symbolically as the span of S is equal to the set of all vectors of the form A1 U1 plus etc. plus AN UN for n some natural number, AI some scalar in the field F, and UI some vector in S. So we let them vary over all possible choices like this, and we look at all possible linear combinations formed by them. I see someone raised a hand. Yes, please go ahead.
Does this still work if S is an infinite set, or do we require S to be finite here?
So the definition makes sense for infinite sets as well, yeah. So here we don't require anything about S, can be finite to infinite. But it's important that each sum of this form is always finite, yeah. So when you talk about linear combination, you always talk about a finite sum of this form using vectors from a set S, but the set S itself can be finite to infinite. We don't care for now, okay? The definition makes sense for any set, but you're only using finite sums to define linear combinations from it. Yeah, thank you for the question. Yeah. Okay, so we have this. Okay, so for any set, we can form the span. And also, just a little technical tidbit. So for notational convenience, we define the span of the empty set to be the zero vector. So the span of the empty set consists of the single element 0. So here there is no deep truth or anything about this. Yeah, it's just defined for notational convenience. As you'll see, it just allows to write theorems and formulas more uniformly without having to treat the empty set separately. Okay, yeah. So it's just convention. We write it like this. Okay. So now we need some facts about the properties of the spans of sets and vector spaces. So for this, we have a few results. So the first one is theorem 1.5. Okay. So let S be any subset of V. Then we say, S be any subset of V where V is a vector space, yeah? Then we have the following observations. So the first one is the span of S is a subspace of V, okay? So note the set S itself can be an arbitrary set. So no matter what set we start with, S itself might not be a subspace, but if you pass to the span of S, you always get a subspace, yeah? So the point to understand here is that if I have two linear combinations of vectors from S, and I look at their sum, it's going to be still a linear combination of vectors from S, for example, and the same for multiplication by scalars, etc. So this is, you can check this quickly using the criterion for subspaces we just gave, for example. Yeah. So this is one. Span of any set is the subspace of V, and two, any subspace of V containing S also must contain the span of S. Okay, so that's another point. So as long as you contain S and you as subspace, you are going to contain the span of S as well. So what it's telling us that the span of a given set is the smallest vector subspace under inclusion that contains this set. Yeah, that's basically another way to formulate this property. Okay, makes sense so far? Okay. So, all right, this is theorem 1.5. We need a couple more facts and definitions. So I'm going to change the screen now. Yeah, let me just give you a second to review it. All right. So now let's talk about generation of subspaces. So definition. Let V be a vector space and S a subset of V. We will say that S generates, or sometimes we can say spans V, this is just synonyms, if we have that the span of this set S is equal to the whole space V. Okay, so this allows us to talk about generation of spaces by a given set. Okay, and also another definition which aims to complement generation. So a subset S of a vector space V is linearly dependent if there exists a finite number of distinct vectors. So this is very important here. People forget sometimes. Distinct vectors U1 through UN in S and scalars A1 through AN in the field F with at least one of the scalars AI not equal to 0. So another important point, such that the linear combination given by all of this, so A1 U1 plus A2 U2, etc., plus AN UN is equal to 0. Okay, so a set S is linearly dependent if we can find distinct vectors in it, some distinct vectors in it, and some scalars, but not all 0, such that the linear combination given by them is equal to 0. So why do we care about this at least one non-zero? Well, because otherwise it would be a pointless, like a useless statement, right? Because if all AI are 0, then of course linear combination of any vectors is going to be 0. So this wouldn't give us any information about vectors being connected, okay? All right, so this is a definition of a linear dependence of a set. And two, so we say that the set S subset V is linearly independent. Independent, sorry. Well, if it is not linearly dependent, yeah? Not linearly dependent. So no matter what vectors we pick from it and what scalars we pick for it, not all 0, we can never get a 0 linear combination, a trivial linear combination. Okay, so this is a notion of independence of a set. And then we have the following theorem. This is theorem 1.6, connecting this some of these notions. So let V be a vector space and assume we have S1, a subset of S2, a subset of V. So we have two subsets like this. Then 1, if S1 is linearly dependent, then S2 is also linearly dependent, right? So if we can find a linear combination, non-trivial linear combination given 0 in S1, then of course it's also in S2 in particular, right? And also if S2 is linearly independent, then S1 is also linearly independent. So this is just the contrapositive of 1, yeah? So 2 is just the contrapositive of 1. So we have these two nice properties that are often used when you're working with sets of vectors, okay? So this is theorem 1.6, and we also have theorem 1.7 about these properties. So let S subset V be linearly independent. Okay, so we have a linear independent set in V, and let V be any vector in V. So, okay, this is small v. Sorry, let me make this more clear. So we have small v. So let this be any vector in V such that V is not in S. Okay, so the vector V is not contained in S. Then the set given by S together with this additional vector little v is linearly independent if and only if we have that V, sorry, let me say it like this, better, easier to say linearly dependent, okay? If and only if V belongs to the span of S, okay? So this gives us a simple criterion to understand when a new vector is linearly dependent with a given set, as long as this given set S that you're starting with is itself linearly independent. So this is a crucial condition. This theorem is not true without assuming that S itself is linearly independent. Yeah. If we didn't know this, this wouldn't be true. So all assumptions are used here. It's important to know that S is linearly independent for this to be true. Okay. Okay. So we have the, yes, question. Go ahead.
Can you scroll down a bit, please?
Oh, you cannot see. Okay. Let me see if I can. Can you see like this?
Yeah, I think that works. Thank you.
Okay, sure. Yeah. Okay. So so we have this, and finally, let me just end with remind you definition of a basis. So we have these two properties: linear independence and generation. And so the crucial definition that plays a fundamental role in analyzing vector spaces is basis. So a basis for a vector space V is a subset of V which is both linearly independent and generates V. Okay. So we have, this is definition for basis of a vector space. So we're going to stop here today, but of course you've seen this notion extensively in 115a. Yeah, so, and you probably know a lot of properties about it. So, yeah, so we'll see, of course, next time I'll recall briefly various properties of bases, because that's very fundamental for understanding vector spaces. Using them, we can define dimension, of course, which is very important for studying isomorphism, etc. Yeah, so I'll review bases and linear transformations next time, which will basically be almost everything we will need. Well, this is like an overview of 115a, right? And then we'll move on to new material. Yeah. So don't worry if you're a bit bored. Okay, I hope it's helpful to just put yourself in the mindset with all these notions to recall yourself about 115A. But if you're bored, we'll soon get also to new material. So I hope everyone will be satisfied in the end. Yeah. All right. So I'll stop here today. So thanks everyone. Yeah. Nice seeing you all. Hopefully I'll see you in person at some point. All right. So I'll see you on Wednesday, same time. Thank you. Thank you very much.